it's a real pleasure today to introduce Professor Sanghyun Lee, and he's an associate professor in the Department of Mathematics at Florida State University. He received his Ph.D. in 2014 from Texas A&M University, and subsequently he was a postdoctoral fellow and research associate at the Center for Subsurface Modeling in the Oden Institute at the University of Texas at Austin. He joined Florida State University in 2017, and his research is supported by the National Science Foundation and the U.S. Department of Energy's Earthshot initiative. So as you'll see, his research focus is on robust physics-preserving numerical models for multiphysics problems. And I will leave it at that. And Sanghyun, the floor is yours.
All right, thanks. Good morning or good afternoon or good evening. Thanks for the introduction and thanks for coming. Again, thanks again to all the organizers for this seminar. I know it's a lot of efforts for putting this seminar together always. I have been attending this seminar time to time whenever I could, and it was always filled with very, very good talks with all different perspectives. So I really enjoyed it so far, and it is my great pleasure to be part of the seminar as a speaker today. And I hope I can also let you enjoy this time a bit. I don't think I really recall a lot of speakers from math department recently, except Anthony Pierce, but I will try my best to entertain you all at this time. So today, yes, I'm going to talk about this phase field fracture towards hydraulic fracking. And here I start from the list of my collaborators. So as John said, I started to learn about this application in 2015-ish when I was a postdoc at UT Austin in Mary Wheeler's group, Center for Subsurface Modeling. Now she officially retired. And yeah, it was also really a joyful time working on this, a lot of petroleum engineering applications. And I also want to acknowledge not only all the collaborators, co-authors, but also all the support that we had from different companies and funding agencies in the past, right? And I also do want to mention this. It was 2018 when I was lucky to join this Banff Burst meeting, which Igor was one of the organizers. Here he is. He's quite young, right? I remember him running around this mountain every morning. And there I really learned a lot, and definitely what I experienced from that meeting influenced my current research path as well. So this is a very good memory that I have in my research path. I'm not sure if anybody in the audience was there. I don't know. All right, so again, so let's start. So here's the outline for my talk. I know it's being recorded, so a quick disclaimer. I don't speak for this entire phase field fracture community. It's a broad, diverse area with many, many experts. I think it's growing, in recent years, again, more. So if I missed citing your work or missed some important works that the other did, please let me know. But also please forgive the omission. It's not intentional, just a result of how much great work there is. All right, so what is the phase field? This is the cartoon that I like to have. Let's assume this is a real fracture. And there are a lot of different interface approaches like XCFEM, discrete fracture network, DFN, cohesive elements, and so on, where they look the fracture as a one-dimensionless object, for example, as a line in 2D or two-dimensional phase in a 3D domain and so on. Phase field is a little bit different. We call this is a diffusive approach. So instead of having a one-dimensionless object, it's lying at the same dimension, so which means the fracture actually has an area or volume inside. So the phi is the variable phase field where I'm going to use for this talk. It is a scalar function which has only value between 0 and 1. Okay, so for us, when phase field is equal to 0, we call this as a fracture zone. And when phase field is equal to 1, it's going to be reservoir or non-fracture zone. And it's not a discontinuous function. We'll have a continuous interpolating value from 0 to the 1 at this diffusive zone over here. And the length of this diffusive zone is now denoted by epsilon. And if you're in the phase field community, this epsilon is a very, very important parameter that we have to carefully analyze. All right, so what can we do? So here are some examples of the phase field fractures. Okay, so here are some lines or interface approaches, and here I'm plotting the phase field value representing the fractures. Sorry for the flipping the colors, but here 0 is the blue, 1 is red. The fractures are here. You can see a little diffusive zone, and you can actually also see some area, inside the fractures. Maybe this will give you a better view of the fracture presented by the phase fields. It is a one continuous scalar function. And there are a couple of things which I want to emphasize here. So I said this epsilon is the length of the diffusive zone. And you can see I have a pretty small epsilon to have a high quality or better presentation of the fractures. You can imagine if epsilon is large, you'll have a very diffusive or non-realistic fracture representation. So it is really important to keep this epsilon small. But at the same time, in numerics and in computations, you have to discretize the space, and you have to make sure your mesh size h is also smaller than epsilon, so you can have an accurate representation of epsilon, right? So, and at the same time, we know if you're using very small h in entire domain, it's going to be too expensive in the computational sense. So for the phase field fracture propagation problems, I think it is really important to have this adaptive mesh refinement techniques. Here you can see we're only refining the meshes near the fractures. Okay, I'm going to talk about this a little bit more at the end of the talk. So now, how do we do the fracking with this phase field? So here, we can start from this energy functional for the brittle fractures. And let's rewind a little bit back to the interface approach. So let's say this lambda is the entire domain, C is the fracture, and omega is lambda minus the C. And this energy functional is now written as the following. And this is the energy balance between the omega here, which is the non-fracture zone, which is written as U displacement, and total stress sigma U here is for the simplicity linear elasticity, and mu and lambdas are the Lamy coefficients. And this is the energy for the non-fracture zone, and it is a balance with the fracture energy as well, where energy of the fracture is written as a Hausdorff measure multiplied by the Griff criteria or fracture toughness value. And a lot of this foundation has been studied by Frankfurt, Marigo, and Bourdin, and this is the great study of the fracture represented by phase field at the later on. So now where is the fracture? Here it comes. Where is the phase field? Yeah, so we have the global functional form, and you can see a couple of main differences, okay? So now, first of all, instead of using the omega here, we're using the lambda, which is now the entire domain, the global domain. How can we do this? Doing by multiplying the phase field function phi here. So why? Because recall phase field was equal to 0 in the fracture. So anyhow, this is defined in the entire domain lambda. When phi is equal to 0 in the fracture zone, this value will vanish. Okay. Same for this fracture energy. First of all, this Hausdorff measure is now rewritten by the phase field energy here as the following, Ambrosio Tortelli functional, and some good studies has been followed up by Mihi, Landis, Karma, and Hughes as well. So here we can also see that energy for the fracture is now extended to the whole lambda here, entire domain in global form. But note that in the reservoir, when phase field is equal to 1, this will vanish, that will vanish. So it is inheriting the energy balance between the non-fracture zone and the fracture zone, but now it's in the global form by employing the phase field values. Okay. So we start from here. But now we extend to consider the fluid-driven fractures in porous media. The main change is the sigma that we had is now the sigma tilde, which was linear elasticity before, but now this is the poroelasticity based on Biot's and Cousy's theory. Here P is the pressure and alpha is the Biot coefficient. So this is the energy functional, which is now coupling the displacement, phase field, and the pressure. So at the end of the day, we're solving this energy minimization problem, right? But we have a constraint. And this constraint is called irreversibility condition, where we only allow phase field to decrease in time, which means phase field value changing from 1 to the 0, which only means the propagation. But I hope we don't get confused here. So it doesn't mean that we cannot consider fracture closing. Right? Fracture propagation is not the same as the opening. So fracture opening and closure are handled by the width not the phase field values. A phase field is just the indicator of the fracture path or the fracture zone here. Okay. All right, so now how do we handle the pressure? So we have a Darcy's law. I don't think I have to talk about Darcy's law with this audience. And this Darcy law will lead to the conservation of mass equation, now which is coupled with the mechanics as a poroelasticity system. Again, the BO poroelasticity theory here. Here, the porosity is now written as 1 over MP plus the divergence of U, where U was the displacement. So now this is the coupled parabolic PDE type of the fluid, which is now defined in the omega R. Omega R means the reservoir zone, okay? Now, how about the fluid in the fracture zone, all right? So in the fracture zone, we still have the same Darcy flow type conservation law for the fracture flow. But now the difference is that we have different physical coefficients. And more importantly, we do not have any coupling with the displacement in the fracture flow by assuming the porosity is equal to 1. Moreover, the permeability is different. In the reservoir, the permeability is given as the given data, but fracture, the permeability has to be computed, which is based on the width computation over here. Okay, I'll talk about this more later. Next, now how do we separate this omega R and omega F? Again, by using the phase field, right? So for simplicity, we can just assume we're multiplying phi to everything in omega R, 1 minus phi to indicate the flow in the omega F. For example, if if phi is equal to 1, this is alive, this goes away. And phi is equal to 0 in the fracture, this goes away, this is alive. And in the mixture, we have an averaged flow in between omega R and omega F. So basically, roughly speaking, this is more or less we're getting the interpolated pressure values between PF and PR through the given phase field. I will not go over too much details, but more rigorous studies based on lubrication approximation for driving the Darcy flow system from the Stokes, the imposed interface conditions, a leak off, you can find and look over these papers for some more details. Okay. All right, so we talked about what is the phase field and how we use the phase field to model the fracture propagation. So now let's talk about why are we using it by showing some numerical examples, okay? So here we have a couple of 3D examples, which has been quite old, but anyhow, the left here, we have these 2 penny-shaped fractures, blue, and we inject the pressure in the middle of each in this heterogeneous media with some random Young's modulus and permeability values, and we can see this curved linear fracture propagation and joining and branching, right? You can also see this adaptive mesh refinement as well. Also the right, this is the famous stress shadowing effect. When the fractures are too close, right, I'm injecting the pressure, and then you can see fractures interact and they curve out while they propagate. So one of this main advantage of the phase field is that the crack propagation here is automatically determined by the energy minimization. We don't need to compute the stress intensity factors or give any ad hoc laws near the crack tip. We don't even have a crack tip over here to determine the fracture propagation. Okay? So that's one of the advantages. So here's also one 2D example where we have several natural fractures. So you are looking at the phase field values, which I showed you at the very beginning. And now I placed one hydraulic fracture at the middle, and I'm injecting the pressure. And you can see the phase field value on the left, pressure on the right. When it's hitting the natural fracture and it's accumulating the pressure again to propagate, it's meeting over here, B, meeting again here at the C. And overall, you can try to plot the maximum pressure values in the entire domain. And you can see the pressure peaks and it goes down whenever they interact with the natural fractures. And you can actually turn off the injection to see the flow back. And we have done some, these type of the studies by looking at the interaction with natural fractures as well. Just one more. This is again with the 2 natural fractures and 1 hydraulic fracture at the middle. And I tried to benchmark one of the examples that Kanu had from different fracture propagation model in one of her papers. And I thought we have quite a similar match. Again, we don't enforce any laws at the crack tip, just we're solving the system that I just showed you in a couple of minutes ago. All right, so what do we have as a challenges, okay? Or for computing all these examples, what did I do? What were the hurdles? So first, to solve this constrained energy minimization problem with irreversibility condition, this is optimization problem, we have used this Newton primal dual active set method technologies. So in our previous publications, we also have used simple penalization, augmented Lagrangian in some other works, but we found that this active set method is quite efficient and works well, including a 3D example. Next, to couple the flow and the minimization problem, we used fixed stress iteration techniques. The idea for the fixed stress is to fix this volumetric mean stress while solving the pressure first, and then solve the mechanics with a given pressure. Okay? And we iterate until it converges, right? So here, this is a 3D example which shows a 3D fracture propagation. And then this is the number of the fixed stress iterations, overall time, and which we can show that it's quite stable overall. For the adaptivity, here we use this predictor-corrector mesh adaptivity idea, which was initiated in this paper. It's simple. We just first solve the fracture and see where the fracture is heading. And then we have to go back and recompute after we refine the region where we know fracture is going to propagate, and we do this for each times. So we can keep epsilon to be larger than h, and also refine only the near the fractures, and detailed studies how this is quite efficient in the computational time and so on. Please refer to these papers. Okay, so furthermore, yes, we saw some advantage of this diffusive approach, hopefully, but this is actually one of the main challenges as well in the phase field, okay? Because first, this epsilon, right? We have to be careful of choosing the epsilon in several perspectives. First of all, in theoretical perspective, we are based on this gamma convergence study, where it has some baseline theories to study the diffusive fracture is going to eventually converge to the interface zone, all right? At the same time, the choice of this epsilon is important to do some numerical studies, because now epsilon can depend on h, the mesh size. And then whenever h is decreasing, we want to make sure you have some convergence in your energy as well, right? Third, I think there are some aspects that epsilon can be a physical constant depending on the material properties, which links to some theories such as the damage zone and so on. So it is a quite still very important and hot area how to determine and how to study this epsilon in the sense of some convergence. So one last thing is then, how do we compute the width, which is going to determine the permeability inside the fracture, which is very important for us, right? So this is the width approximated as the jump of the displacement. And note that in the phase field, it's diffusive approach, so we don't actually have a sharp interface. So here the challenge lies on the fact that we have to approximate the normal vector in the fracture interface, and then we have to first define where the fracture interface is, right? So here we have utilized the idea of the level set, so we can define where the fracture interface is. And after that, we can approximate the normal vectors. So we can do this whenever fracture is curved linear and so on. And I know a lot of different studies on this with computations. I looked at all these different papers. We also have a couple of papers on this, and one we have recently followed up. So once you define this gamma f, the interface of the fracture, and you approximate the normal, you can compute the width. But note that we don't have a displacement inside the fracture, right? Inside the phase field, when phase field is equal to 0, we're not solving for the mechanics. So there we have to do some interpolations. So we're solving this width problem. So we are solving this penalty-based elliptic problem to interpolate the computed width inside the fractures, okay? So that's what we do. So here are some examples of validation of this framework by checking the width with the Sneeden's test. So it is showing that we reduce the mesh size h, and we can see some convergence of the width value in this 3D penny shape with a pressure injected we can converge to the analytical solution of the Sneeden. This is some time ago. Also, we have checked with the KGD test and so on. So for all spatial discretization, I use finite element methods, okay? And if you're in finite element method world, there are a lot of numerical instabilities which often arises, especially when you're doing multi-physical system, coupling mechanics, pressure, width, phase field, nothing is going to be obvious. You have some implicit condition to consider, maximum principle locking, local mass conservation, and such, right? So for this time, I only want to focus on this local mass conservation. So in particular, let me recall one of the well-known benchmark test case, which is called Terazagi's benchmark problem for the poroelasticity. I think we all know this if you're in this poroelasticity business. So I omit the given details of the setup here, but I just want to point out that if, finding everything good, or if using all the coefficients that they provided, including the smooth permeability K, and I'm using the classical continuous Galerkin finite element Taylor-Hood to ensure the MSUP. So this is the thing that you can easily find online, if you're looking for finite elements. You'll obtain some desired convergence rate and everything is good. You'll match the analytical solution and so on. However, if I tweak the problem a little bit, let's assume we have a heterogeneous layer of the permeability K, then we might see some oscillations near the interfaces. And this is well known, right? This is due to the lack of local mass conservation for this classical continuous Galerkin method, or lack of handling this discontinuous material properties. So there are many, many remedies of this, but we have developed and analyzed this novel enriched Galerkin methods, where the basic idea is to just enrich the classical continuous Galerkin method with only 1 degrees of freedom per elements to satisfy the physics that you desire. So for example, we can just add piecewise constants, only 1 per element, which has been well studied through Shiu's paper, and we followed up with analysis and different applications. So we can ensure the local mass conservation with this EG methods. Okay, and then we are using this enriched Galerkin method to discretize my P. For the displacement, I'm not adding a constant, but I didn't bring it here, but we are adding a specific vector per element in the displacement formulation, so we can ensure the locking free. The advantage of this enriched Galerkin is that we have way less degrees of freedom compared to the discontinuous Galerkin method, which is another popular one to ensure local mass conservation, locking free. It's all good, but I think it's just too expensive, for satisfying these properties that you wish to have. So I think this is EG is the cheapest in terms of providing, these physical properties in the finite element framework. So this is what we use. And then if I revisit this example, we don't have oscillations with this enriched Galerkin method. And briefly speaking, we don't even have the locking phenomena for the mechanics. Locking is the thing which happens when your lambda is large, or Poisson ratio is going to 0.5, and the material becomes incompressible. So we can get over these issues that when we have a multi-physical problem. This EG methods is one of my main field. This has been applied to the different type of physics in recent years. So if you're curious, please take a look. So I think one of another advantage, of this phase field is that also it is easy to extend to include other physics, because it's based on continuum approach. And coupling with other applications are also not too complicated, because passing along the phase field value is just a scalar function, right? And it's also very diffusive. So let me show you some of the works where we have put some efforts in coupling different physics and with different applications, right? So on the top of what we had, like phase field, displacement, pressure, width, all the numerical algorithms, enriched Galerkin method, now we can couple with the transport equation to consider like proton concentration in the fractures. Here we're using this nonlinear fluid based on the power law, and we can try to find, proton transporting in given media. So this is an example of the transport viscous fingering with our enriched Galerkin method and adaptive mesh refinement techniques. And this was imported to our phase field fracture propagation in early time to see the proton transport inside the fracture in a 3D penny shape. Also we have two fractures joining and branching, and you can see or you can track the concentrations and so on. Okay. We also have extended the model to consider two-phase flow by adding the saturation. A lot of mathematical work has been done in this paper to have the relative permeabilities, capillary pressure in the fractures, and so on. And here's one example that we had in the past. So this is a large domain. You're looking at the phase field values. The natural fractures were given by this microseismic data. And I placed 3 hydraulic fractures in the middle of this domain. And we're injecting, and we're doing some multi-stage fracking. So you're looking at the pressure values on the background. You can propagate the fractures, and they can join, and they can merge. This is what we have done using our simulator. So also we coupled with optimization techniques. So for example, what we can do is, can we try to find optimal locations or the distance between the pair of fractures to maximize the production in heterogeneous media? This has been, studied in this work. And also we can perform some type of history matching to find the given heterogeneity in the domain with the fracture profiles. Maybe I think we can do way better work nowadays with using the machine learning and so on. So this is one of the most recent work where we have considered this THM fractures for targeting the enhanced geothermal systems. The difference highlights the total stress now includes the thermal effects, which is the theta here. Okay, the following the BO inclusive theory again. So we can also employ the diffraction system for the energy balance equation for the temperature. But we have linearized some terms inside the time derivative for the simplicity, okay? But this is a fully coupled process between temperature, pressure, and the mechanics. Here we also have the coupling temperature terms in the pressure equations as well. Okay. Then this example shows one scenario of enhanced geothermal system where we have some natural fractures and injection production wells. First, we can see the pressure values, and we can see the injection of the cold water, cooling down the domain to the production well, which means the injected water observed the heat, and we can see some width changings and so on. Not really fracking here yet. So here's a simple example of the fracture propagation, okay, but with different temperature of the injection field. So this is the phase field. You will see the pressure moving on, but now the difference is in here. Hot water injection and cold water injection, okay? It's hard to see the difference in this scale, but if you zoom in, you can actually see the difference of the fracture length. You can see a little bit more propagation whenever you're injecting the cold water due to we have a little bit more opening of the width, okay? And then I don't think this is a big surprise. I found some papers that they have a similar findings from the lab experiments and the field test as well. And also, this is not a magic, right? This is definitely due to all the modeling perspectives. So what we are doing here is, what happened here is due to the interface condition that we impose. So in the interface, we have to impose certain conditions, and sigma tilde is the whole thermopolasticity thing, which we have in the reservoir domain. And then sigma F is the total stress that we have in the fracture. So we don't have the mechanics, and we have the specific coefficient of the temperature near the fracture following this Zattari's work. From here, if you try to write down the displacement formulation, before we go into the weak form and such, the thing is we have this theta minus theta 0, which theta 0 is now, residing or reference temperature. And this sign of this thing can be changed whenever you're injecting the hot water and cold water. And this is the reason it makes the difference. Furthermore, we also have extended to couple the chemistry like THMC. But first, this page is mostly focusing on the acidizing near the wellbore. I just brought a couple of numerical results. We have compared with some experiments, and we have tried to look what happens to the acidizing near the fracture, near the wellbores and so on. This is the work which has been done by Mohammed, who's now in Exxon. We have tried to couple this IPAX, which is the name for our phase field simulator, to the IPARS, which is our UT Austin's in-house code reservoir simulator. So we don't have to reinvent the wheel for the compositional flow. I know how complicated that is. So we try to couple the framework. Here, the propagation of the fracture is not considered, but you can simulate and present the saturation of the water. Also, we tried to couple this with a phase field code that we call it IPAX to the CMG, one commercial software, right? And tried to compare with the CMG's fracture model from some years ago, JAM. And we tried to see what is the difference, what can we do, and how important this fracture width is. And, due to some difference in the fracture width computations, definitely it's leading to the different bottom hole pressure and eventually the propagation, the production as well, right? So we're trying to see if this is a worth investigation for phase field to have a curvy fractures in a heterogeneous media near the wellbores. Lastly, I think we have coupled our IPACs, the phase field fracture, with fluid structure interaction to study the width problem more carefully. This algorithm is suggesting that we first compute the width from the phase field, as I just told you some time ago, and then we can reconstruct the geometry based on the width deformation. And then with this new geometry, we can try to solve this FSI, fluid structure interaction problem, by considering the Stokes fluid inside, not anymore the Darcy. Okay. And then here is some results of the temperature and the pressure. You can see now we have a different geometry of the crack. And the advantage of this framework is that we can see and some convergence of the width values, and where we can see some difference in the width or crack opening based on different temperatures and so on. Okay, so anyhow, this is it. So let's conclude. I hope I didn't went through too quick, but I didn't want to use too much time as well at this morning. But I didn't go through too much details, but I tried to a little bit, showcase what phase field can do and what are some advantages of it. So I hope I could demonstrate some potential, all right, of this phase field approach for treating some practical applications. I think the advantage, if I try to summarize, we have this high fidelity numerical methods. It's continuum and diffusive approach, so it's easy to extend and handle multiphysics, in my opinion. And the fracture propagation is driven by energy minimization problem. I think this is an advantage. Definitely we have some limitations as well. High fidelity means computational costs are expensive, but I think we pay for what we get. And still, we have many challenges to discover, which can be some future directions. So some papers or some research that I thought was very interesting in recent years was, okay, we are looking at the phase field community is looking at the fracture nucleation or how to initialize the phase field fractures. And this is quite important thing in the phase field fracture community. And some scaling issues, this epsilon h, how do we handle large scale fractures? Or do we need more physics, right? Like shear fracture and so on. And there are some more benchmarks that we want to match and compare and so on. So this is what I'm looking at, right? Do we need more physics, more accuracy, more efficiency, or do we even need less physics, right? I think this depends on the applications that you're looking at. And I wish I can tackle some real production scenarios in some time, but as you can see, I'm sitting in this small math building office 01 box. I don't know, some simulation that I've done might be a joke for you in the engineering, but I think this phase field can, better fit to the near the wellbore problems. We have a very precise fracture representations. And I don't know, coupling with this machine learning can expedite the process and so on. So now this whole code is based on the finite element library called DIL2. This IPAX is the name of the code that we have. And I have to acknowledge my funding from NSF and DOE. And yeah, thank you for your attention.
Hey, thank you, Sanghyun. That was awesome. That was really clearly presented, complicated subject. And I think I don't know whether you can see the chat or not, but I think you've dealt with Igor's first issue is what is the future? What future directions are you taking? I think that's why.
Yes.
And you touched on his question.
Yes.
Can you model shear slip as well as frictional contact? Can you elaborate on that?
Yes, yes. I think this is what exactly I'm looking at these days because I really see a lot of crack opening happens from the shear slip, right? And then Fenfei and Chu, these are also my friends. I think they have looked at some of the work which I cited over here. I bet there are more works. I was also talking with some other people from Brazil, in the last SciAm Geoscience meeting. So I think this is what we can handle, but definitely more careful approaches required because of our diffusive zone thing over here. Yeah, what is the future? I don't know. This I have to really interact with engineers, field practitioners. I think the strength of this phase field is really lying on the near the wellbore. I cannot say I can do, like 1,000 fractures like DFN does, or I cannot do like 1,000 kilometers. But when it becomes to smaller regions, when you want to see some precise fracture formulations or understand a little bit of science, that we can understand with all the uncertainties, I think phase field is the good fit. So this is where I'm looking at. I want to a little bit more investigate on uncertainties nowadays, because uncertainties will change a lot of things in the fracture, data simulation, and so on. So that's what we're looking at.
Cool.
Uh,
And Adrian has a question as well, and
yes.
his question was that you've shown that you can handle an hydraulic fracture interacting with a natural fracture if the angle exceeds 30 degrees. What happens if the hydraulic fracture approaches a natural fracture at a
Ah,
smaller angle than that?
yeah,
And
yes, yes, yeah.
maybe you could address that problem.
Yes, I didn't bring here. I know there are many good papers on this validations, right? Whenever fractures are in different directions, I think Andrew Bunger, if I remember correctly, he had some also papers on here. Yes, we did benchmark. So we do have penetration depending on the condition of the fractures, the angles. Um, yeah, I have to say, yes, we can do this. We try to validate or benchmark a lot of existing works, and yeah, we can handle that quite. I mean, not exactly the same like in the point wise, but in general frame of work, yeah, we can do the penetration. If you impose the right conditions and so on. Yes.
Okay, very nice. At this time, oh, we got a thumbs up. Okay, so
Thank
no
you,
more
Adrian.
questions, but you got a thumbs up, which is a great sign.
All right.
And so, pending no further questions, I really want to thank you for this presentation. As I said, it was really clear and it shows significant practical application. And so
All right.
thank you for doing this.
Yeah, please let me know if you have some further questions or remarks or comments. Yeah, here's my email, here's my website. Please let me know. And thanks for coming again. Yeah. See you later in somewhere in the near
Okay,
future.
thanks a million.
All right, bye.
Okay,
Thanks,
see
John.
ya.
Thank you, John.
That was really great. I
Yeah.
mean, it's such a complicated topic. You mixed equations and demonstrations really well.
All right.
Congratulations. That was very
Thank you.
clear.
I hope, yeah, I didn't lie too much, but
Well, we all say that after a talk. You know,
you know what I mean, right?
we all say that. It was
Yeah,
great.
yeah. Yeah, we don't really show all the messy kitchen after showing the nice
Yeah.